Swayam Prabha. Digital India. Educated India.
Welcome to Module 3, Lecture 4. We looked into mineral admixtures, some of them in the last class, namely fly ash, ground granulated blast furnace slag, rice husk ash, and silica fume. Also, we had some discussion on metakaolin and pulverized fuel ash in general. We looked into the characterization and basic particle size distribution and some essential properties of those materials individually. Now, this lecture we shall be looking into their how do they react, because we define them as pozzolana as a class, many of them. Of course, you can have non-pozzolanic mineral admixtures as well. We will have a short discussion on those, something like limestone powder. Some of them are inert, but here of course, right now we will concentrate on pozzolana. So, how do they react? Hydration of pozzolana we will look into. We will look into the way they refine the pore size of the cement hydrates and improvement in the microstructures that they bring about in cement paste, mortar or concrete, and then setting and hydration of this material, their water demand in the fresh state, etc. So, chemical reaction, something like this is one of the possible reaction, chemical reaction of these materials, the silica component of it, mainly the silica component of it. The silica reacts with calcium hydroxide to form the calcium silicate hydrate. Maybe 100 grams of silica reacts with about 185 grams of calcium hydroxide to produce 285 grams of calcium silicate hydrate. Well, this is one of the reactions. There are several other proposed reaction or possible reactions suggested in literature, but this being the simplest, we can understand something like this must be happening, but finally, the product formed is calcium silicate hydrate. It may not be having exactly this formula, some other formula, but generally calcium silicate hydrates are formed. This silica is inert initially in cement. When you add with cement, initially the silica is inert. If you directly of course mix with lime, then the reaction can follow with lime itself. But if you recall that you see this lime reactivity test, we use lime together with silica, and the demolding time was about 48 hours, which means the reaction do not occur very rapidly in this particular reaction, for this particular reaction silica and lime, and it takes about 10 days of hydration before we do the actually test. So, the reaction process itself is relatively slow, but when you add it together with the cement, then cement does not have lime directly, but when it reacts with water, the C3S and C2S, they produce the lime. So, lime is not available initially, therefore, silica will remain inert. All right. So, calcium hydroxide when liberated, right, and one can actually calculate out, it will be 0.285 CH, because we know the stoichiometry of cement reaction, C3S reacting with water, it forms CHS of some form plus of course, CH that we know, and similarly C2S also produces C2S also produces CH, and this we know, stoichiometry we know. So, from this stoichiometry we can calculate out that calcium hydroxide liberated is 0.285 C is the amount of cement into H is the degree of hydration. The silica consumed would be about 0.15 CH, because for 285 CH liberated is 285, the silica is 185, lime is lime divided by the final product is of this order, and it would be one can find out that it is about 0.15% of the CH will be the silica consumed. So, one can actually find out how much percentage of silica is consumed. So, it is about 15% of the cement that is hydrated, right. That is what it is. So, if H is equals to 1, it is 0.15 C, that is stoichiometric upper limit. The maximum 15% of the cement reacts 0.15 C is the maximum silica that can be consumed by cement, pure silica 15% by mass of the cement that can react with the cement at full hydration. If it is partially hydrated, lime liberated will be less and it will be even lesser. So, one can actually calculate out how much maximum silica it can consume, that turns out to be 15%. Now, specific gravity is 2.25 and one can actually using same kind of Powers model as we have done for cement, one can possibly show that the capillary porosity will be given by WC minus 0.36 H, and this was already there if you recall in case of cement alone, but when you have silica fume one can see that it will come as 0.44 S divided by C, where S is the silica and C is the S is the silica that is reacted and C is the cement. So, this term increases, this term remains same, this is the space occupied space left unoccupied by the water filled space which remains unoccupied after hydration product has come. So, one can see that actually capillary porosity will be lower, because this value is higher, the denominator is higher, and therefore, capillary porosity reduces in case of silica or any pozzolana consumed by the cement. So, there is a reduction in capillary porosity that one can calculate out. This comes out to be this. One can do this exercise, it is not very complex, but then this is one of the reactions actually. This is still, this is not the acceptancy of this has to be seen, because the reactions are not really fully known and things like that. However, one thing we understand from this exercise that capillary porosity will reduce. If one looks at the scanning electron micrographs, right, hydration after 7 days, one could see that the spherical fly ash particle, this is with in the mortar, spherical fly ash particles has produced a number of CHS and they look like cotton like things, the number of CHS has been produced, and this is what one can see from scanning electron micrographs, and similar more such hydrates would be seen, in the 28 days. So, when 28 days more hydrates are formed, 7 will be very little, but 28 days you will see lot of hydration product actually the CHS formation. So, if you distinguish from 7 to 28 days, 7 days much lesser of this would be there, and 28 days you will find more of this hydration product that has accumulated. So, little actually 7 days not much is seen, but 28 days you see lot of hydration product. With PFA, this is a model, for example, you have a Portland cement grain, let us say, and the CHS, right, at early age the CHS has come out, CHS layered structure has produced, which we have seen earlier when we looked at cement hydration process. This is the pulverized fuel ash, which are generally, that is fly ash or similar things, which are generally spherical, and they are there in the initial stage. So, this CHS has formed and calcium hydroxide will be now liberated. Initial age, there is not much of consumption of this PFA, but in the later age, if you see lot of this would get consumed and more of this hydration products. So, lime would be liberated in later age, lime will be liberated, and these spheres are still intact, not really much, but the lime has come and lot of CHS has actually produced. So, Portland cement grain now is become much larger with its hydration products surrounding it and the lime being there in the solution. And in mature age, this lime will start consuming this PFA, and spherical PFA particle will get further consumed and reduce down the porosity, capillary pores present in the cement hydrate system, capillary pores present in the hydrated cement system, right. So, this if we look at it sequentially, first stage is this, followed by next stage, the lot of just initial hydration has occurred, followed by the hydration product surrounding the cement particle, the lime is also there, and then in matured age it will come out, some of this will react and all of them would actually constitute the solid phase, which will bring down or lower down the capillary porosity. So, this is the model accepted for any one of this material. And if you look at the pore size distribution PSD with fly ash, this is what has been tested by people PSD, then you see 28 days with different percentage of fly ash has been seen. Control is here. So, control is the circular one, it is here, right. Control is somewhere here, and if you see the control, it has got penetration, control okay, control will have the control will have this case there are 3% shown. In fact, this is 10% PFA is this particular one. So, you have got penetration volume at 28 days, penetration volume, more volume penetrates as far as 10% is concerned. This one is triangle with 20% PFA, 10% PFA, 20% PFA, more volume, more of volume, pores would be larger pores and with 30% PFA, 30% PFA is also somewhere close to this. So, 10%, 30%, 20% and 30% is somewhere here, and 10% is somewhere there, control is somewhere there. So, it shows control shows lesser porosity, in fact, initial 28 days for particular results, and let us see what happens in the long run. With rice husk ash, this shows with rice husk ash the control is higher, this shows better results. This is with 30% rice husk ash, which shows much lower porosity overall, because this is a measure of the porosity, this is measure of in a way is the porosity, more the volume, more is the porosity, less. So, therefore, this is less porosity and particle sizes are also finer. So, rice husk ash seems to perform better than fly ash at 28 days, and if you look at slag with 70% slag and 30% slag. So, 70% slag is somewhere here, higher porosity, 30% slag seems to perform better, but 70% slag shows lesser pore sizes reduces, although porosity seems to be somewhat higher. So, some ideas of the pore size distribution measured with mercury intrusion porosimetry is shown. Some idea about mercury intrusion porosimetry is shown, right. Some idea about mercury porosimetry, mercury intrusion porosimetry is shown in this results, right. So, what we have observed is that fine pozzolana such as rice husk ash reduces the porosity more and refines the porosity more by 28 days. Whereas, if you look at slag, higher percentage of slag do not refine, although it refines the pore all right, but total porosity is still more compared to let us say 30% slag, whereas fly ash 10, 20, 30% they do not, the pore refinement is relatively not much compared to without PFA up to 28 days. Let us follow it up, pore size distribution curve with and without silica fume. Now, if you have silica fume, then there is a significant change, because it is really fine, it is very fine. Without silica fume, the pore size distribution is something like this, and with silica fume the pore size distribution is the next one as you shown. So, you can see that the pore size distribution sizes become smaller with silica fume, and without silica fume sizes are less refined, and the volume of the pores are also more, So, fine pozzolana, very fine pozzolana, they would actually refine the pore and make the sizes finer, and also they would reduce down the porosity, whereas relatively coarser pozzolana like fly ash, it does reduce, it would reduce this effect much less by say about 28 days, but in the long run perhaps it would be, reducing the capillary porosity to much larger extent. If you see the setting characteristics are related to initial reactions, and generally no adverse effect on either initial or final setting time has been observed. With any one of those material, hardly any effect has been seen on either initial or final setting time. Setting time can be affected when the mineral admixture materials contain sulfates. You see, because sulfates is the first reaction, C3A reacting with CSS bar, that is the first reaction to form ettringite, calcium sulfoaluminate, calcium sulfoaluminate. Now, this is calcium sulfoaluminate are the, these ettringites are the, so if there are sulfates, this can create some problem, and this can interfere with ettringite reaction, but usually this is not a very common phenomena, they do not adversely affect the initial and final setting time. Some results of fly ash, setting of fly ash, the fly ash is available. For example, if one does a ball penetration test. Now, in ball penetration test, what you do is the effort required for ball to penetrate, a standard ball to penetrate in the concrete is measured, and if it is above, let us say if it is more than, let us say this corresponds to about 3.5 MPa, then it is in 3.5 MPa effort corresponds to initial setting time, final setting time corresponds to 27 MPa. So, if you look at that, this is control mix, that is no fly ash, this one has no fly ash, this is with fly ash. So, what is observed is that initial setting time has been delayed by fly ash. It is for some, the cement was type 1 OPC, that is your Portland cement, and this was some type C fly ash. So, some cases it can delay the initial setting time, and the final setting time also can be delayed a little bit, but this is not very significant, this is not of very significant importance. It is only seen in some cases, most of the cases setting time is not affected adversely. In other words, initial setting time is not shortened, not reduced by addition of mineral admixtures like pozzolanas, pulverized fuel ash, or just fly ash as they are, or silica fume, but final setting time in few cases can get elongated, but usually does not extend again beyond 10 hours. So, not much adverse effect is seen as far as setting is concerned. This is with rapid hardening cement, that means now the cement has changed, and rapid hardening cement itself gains the strength very fast, and you can see the time is still within 6 hours, although without the fly ash it is about 5 hours. So, do not really go beyond 10 hours, and initial setting time there of course, is an increase. Without this, the initial setting time would have been 4 hours, but this is about 4.5 hours. So, not much change, and similarly in the previous case, if you see this also do not go beyond 10 hours in any case. So, in the time frame they do not make a great change or adverse effect. So, everything is within 10 hours. So, the final setting time is within 10 hours and initial setting time is not less than 30 minutes. So, they do not shorten the initial setting time and do not elongate the final setting time too much to go beyond 10 hours, because normal cement have final setting time much less than 10 hours. So, that is why they do not affect setting time adversely. The other issue is heat of hydration. Heat of hydration is lowered depending upon the mineral admixture itself. For example, fly ash would lower it significantly, it will lower it significantly, and it is one of the places where it is used. Fly ash is used. One purpose of using fly ash is to reduce down the heat of hydration. Both fly ash and GGBFS would reduce the heat of hydration. They reduce the heat of hydration because they do not react very fast. There are two effects. One is a dilution effect, because if you have cementitious, consider total cementitious material, had it been alone, cement alone, then it would have reacted and produced heat of hydration, but now part of the cement has been replaced by the pozzolana itself, like fly ash. So, therefore, there is a dilution effect. So, heat of hydration in the initial phases will only be contributed by cement, right, and that is why heat of hydration gets reduced. Fly ash reacts relatively at a slow pace, generates rate of heat generation, therefore, is reduced down and it is spreaded over a longer period of time. So, effect is much less. So, both GGBFS and fly ash, they reduce down the heat of hydration. Silica fume of course, is highly reactive, hence rate of hydration is also increased compared to FA or GGBFS, hence heat of hydration depend on mixed proportion. If you have high cement, obviously it will try to produce more heat, and it also depends upon how much is your C3A, because C3A is the major contributor to heat of hydration. It is the major contribution, its major is the maximum, it produces the maximum heat of hydration, that is what we have seen. So, some comparative diagram we can look into heat of hydration. For example, fly ash concrete control mix, if you see time of placing in days versus the heat of hydration, then control concrete produces more heat. This produces at the same time, but the amount of heat produced is much less. This must be in joules per kg. So, this is much less. So, heat of hydration produced is much less, and temperature, sorry, the previous one is also temperature. This should be in temperature rise that is showing. So, temperature rise is much lower with fly ash, and here also the temperature with OPC 360 kg, this is OPC 265, OPC 265 kg, right, OPC 265 by 150, this one is OPC 265 by PFA 150 kg, right. So, this is the one, and this is ambient condition is somewhere here, relevant ambient condition is somewhere here. So, this is 265 OPC, this is OPC 265 plus 150 kg of this is fly ash is 150, and ambient condition is here, ambient profile, relevant ambient profile in two cases, this is what is shown. So, actually temperature rise is much less when you use fly ash, and this diagram also shows the same thing. For example, this is the top surface of a grade level, top of a foundation. So, it is a raft, thick raft, 4.5 meter thick raft, 4.5 meter thick raft, bottom of the foundation is here. In this direction is the temperature. Now, fly ash concrete has got the maximum temperature somewhere here at its center, whereas this one is controlled without fly ash will have much higher temperature, and slag concrete is still lower than the fly ash concrete. So, generally temperature at the center is maximum, because dissipation will take place from here, dissipation will also take place to the ground, but center temperature rise is maximum, and in this particular experimental results as is shown, the slag shows the least temperature followed by fly ash, and control concrete shows the maximum temperature, control concrete shows the maximum temperature. So, as you can see that they really reduce down the heat of hydration, both slag as well as fly ash, both can reduce down the heat of hydration. Setting not adversely affected, but heat of hydration is reduced by use of these particular materials. Water demand, let us see, because do they affect the workability, water demand, right. So, now when it is spherical particle like fly ash, they ensures better packing of the cementitious system, and also there is something like they ensure there is some amount of ball bearing effect. That means, on circular or spherical particle, all other particle can move very easily on top of it, it can roll over. So, this is called ball bearing action, and this material fly ash can exhibit this ball bearing action, because they are they are spherical. Better packing characteristics, and hence less water demand. So, water demand reduces because of better packing and also ball bearing action. So, they make the concrete somewhat flowable, they make the concrete somewhat flowable, concrete or mortar somewhat flowable. So, in a way water demand reduces with fly ash, water demand reduces with fly ash. Slump can be although lower. If you get 100 mm slump without fly ash, that is equivalent to about 75 mm slump with fly ash. The cohesion is similar, the consistency would be similar, workability, that is your effort for compaction would be similar. However, the slump can be slightly less, because they are sticky, it is a little bit sticky with the more similar consistency. So, as a result, it has been observed that slight slump can be lower, although cohesiveness is same. So, 100 mm slump with no FA is equivalent to 75 mm slump with FA. So, therefore, 25 mm slump reduction would occur, although water we find that cohesiveness is same. Particle fineness will have some effect. Finer the particle or finer particle is more, the water demand would change accordingly. In fact, below 45 micron, one of the characteristics of way of measuring the fly ash is the percentage of particle passing through 45 micron or percentage of particle retained on 45 micron. If it is more, passing through is more, that is a better fly ash, because that is finer, and fineness performs better, right. Spherical particle content has also some effect. More the spherical particle content, it has been seen that water demand reduces, because ball bearing action will be more, packing characteristics would be better, and therefore, less water is required to fill in the pore space within the cementitious material to make it consistent. So, consistency, standard consistency, if we or similar thing, if we conceive, the amount of water required will be less when you use fly ash with more spherical particle and more fine particle. Let us see, some diagrams are available. If you look at this diagram, this is 0 fly ash control, fly ash particle greater than 45 micron by mass. So, if you increase the particles more than 45 micron, free water required in liter per meter cube of concrete, you can see that this increases with 10% fly ash. If you have 10% fly ash and 10% is particle greater than 45 micron, water demand is somewhere around 190 liters, right. But same when you have particle retained on or for coarser than greater, coarser than 45 micron is more, about 50%, then your water demand will increase. So, finer the particle or particle passing through 45 micron, if it is more, retained is less, retained more means poorer, more water demand, passing more is less water demand, and this effect tends to, water demands tends to reduce when you use more and more fly ash, and it just goes on, more fly ash, less is the water demand, fine fly ash, less is the water demand. So, therefore, this seems to be, there is this seems to simply increase. So, up to 50% if you look at it, water demand seems to reduce with the fly ash, and it also seems to reduce with the fly ash particle being finer, particularly passing through the 45 micron. If it is more, that is better. This is proportion of spherical particle. Now, this is pure Portland cement, no fly ash. This is the proportion of spherical particle and this is the water demand by the mass of binding agent to give you same kind of consistency, both cases same consistency. So, more the spherical particle, water demand is much less, same kind of consistency. For example, if you have about 80-90% of spherical particle, you will need only 22% water to give you a standard consistency sort of thing, whereas if it is only 20% spherical, you will need 30 to 33. Control is of course somewhere here, control is somewhere here. So, higher particle spherical particles, more the spherical particle, lesser will be the water demand, lesser will be the water demand, right, lesser will be the water demand. Okay. So, this is how fly ash affect the water demand. If it is silica fume, they are of course spherical in shape and they do ensure better packing, hence more cohesiveness, ball bearing action is also realized, but they have very fine size and with their large size, single large size being more, they themselves may require a little bit of more water for wetting. So, packing both these effects act together. Slump can be lower, although cohesiveness is similar, quite lower like fly ash itself, and you have relative water demand. There is an expression like this, where H is for this kind of material, pozzolanic material, where H is a factor indicating relative water demand. If it is all cement, 100% cement, 100% cement, this H factor is not there, but this term will be simply 1. C, put C equals to 100, this term is 1, this term is 1, right. C is the cement content, P is the in percentage. So, normal consistency of PPC. So, if you have normal consistency of PPC minus 26, that is with the H is a factor indicating relative water demand. If the consistency is low, less water demand will reduce down in case of material like silica fume. Hence, reduction in water demand, that is what we have seen. GGBS has no such effect, because it is irregular in shape. GGBFS, there is no such effect, because it is irregular in shape. So, if in the previous expression, if the standard consistency of the PPC is less than 26 or it is 26, if it is 26, then this term is 0. If it is less than 26, then you will get a reduction in the water demand, but if it is more than 26, you may not get. So, for PPC, the P depends upon what is the value of P, standard consistency of PPC. If it is better than 26, this is an empirical equation. Something of this kind can be understood, that if you have the PPC for Portland pozzolana cement, this were directly adding fly ash or directly adding fly ash always reduces the water demand. PPC, there is some amount of grinding. So, it will depend upon the standard consistency of PPC that you obtain. If you have less consistency of the PPC, you will get less, water demand will be lower, and this is an empirical equation. It is related to 26% standard consistency. Now, overall, if we can sum it up, fly ash, spherical particle, thus ball bearing action, hence generally reduction in water demand. PPC or slag cement will have somewhat different properties or different performance in these terms, but fly ash, when you add to the concrete directly as binaural admixtures, you will get it something like this. GGBFS, no such effect you will get, because they are irregular in shape and therefore, you will not get reduction in water demand. Silica fume, very fine and large surface area, but dispersion results in uniform concrete. So, therefore, fly ash is the one which almost reduces down the water demand, almost act like plasticizers. I mean, not to that extent, but something plasticizing or water reducing effect is very much there. And rice husk ash has a other kind of problem, because it has got a cellular structure rice husk ash has got a cellular structure, therefore, water demand is increased due to cellular structure. So, it increases causes increase in water demand, rice husk ash causes increase in water demand due to cellular structure. Mixed design methods actually allow for reduction in water content if you are using fly ash. For example, in a slump range of 10 to 30, if you use fly ash 20%, the water demand can be reduced by 10 kg per meter cube according to the British practice of Department of DOE British practice. So, in this one you can reduce down. So, therefore, it is in mixed design, if you are using fly ash from outside and depending upon percentage of fly ash, you can reduce the water demand depending upon the slump, original slump of the concrete. So, if you look at higher the slump, the reduction is more. So, control concrete had more slump or range of slump is more, you can reduce the water more. More the fly ash, you can reduce down more. You see, it is increasing along this direction, increasing along this direction and increasing along this direction. So, water demand can be reduced if you are using fly ash, because it has got some plasticizing effect, but it will also depend upon type of fly ash. If you have 45 percentage passing through 45 micron and how much spherical particle is there, this is an important aspect. No such things are seen from GGBFS or no such things are seen from GGBFS or no such things are seen from GGBFS or it's in fact GGBFS will give you a opposite action. It is it doesn't it gives you an opposite action, and it causes an increase in the water demand, in fact, because of its irregular and angular shape. Silica fume, as we have seen, it reduces down. So, therefore, I mean there is nothing like no codes allow you to change. Now, one issue which we have not discussed so far is the issue of we have not discussed so far is the issue of superplasticizer demand, superplasticizer or plasticizer, water plasticizer or superplasticizer demand in case of fresh concrete. So, when you have fly ash, it does not increase. Rice husk ash increases the superplasticizer demand, significantly. Silica fume on the other hand, silica fume also increases water reducing agent demand, and GGBFS also increases demand for water reducing agent. Now, rice husk can increase it to such a large extent that rice husk ash can increase this demand to such a large an extent that it may not be feasible to use this material, because there are negative effects of using excess water reducing agent. In fact, it can affect the setting characteristics significantly if you are overdosing it. So, this is a problem. The compatibility of rice husk ash with the superplasticizer is a problem, because it is cellular in nature, and therefore, it has got very large surface area. You can recall the blend surface was very high in case of rice husk ash compared to even silica fume. So, you have got, when you have got very large surface area, specific surface, this results in, this usually results in adsorption of large quantity of water reducing agent. So, demand for water reducing agent increases significantly when you are using rice husk ash on the extreme, and fly ash is on the other extreme, which actually reduces down the water demand. So, they have a plasticizing effect. So, if you use superplasticizer, that such kind of problem do not come with it. Silica fume although makes the cement based material or concrete system more cohesive, since its surface area is very large, because of its fine size, silica fume also tends to increase the superplasticizer demand. So, normally one has to look at the compatibility issue of superplasticizer with the silica fume and cement system. In fact, as you go on increasing the proportion of the silica fume, the demand for superplasticizer increases even more, and thereby the dosage required increases. So, optimal dosage is usually is much higher, quite often can be quite high in case of rice husk ash, and that is why it creates a little bit of problem while using them. Right. So, this is as far as the behavior in fresh concrete is concerned. So, what we have seen is, number one, we have seen that to start with, they do not affect the setting characteristics. Setting characteristics minimum effect. Heat of hydration, lowered by fly ash and GGBFS. But may not be SF silica fume, and RHA may not be as effective as fly ash and GGBFS. The next would be, these are the two main initial important characteristics of the fresh state. The next would be reduction in water demand, what we have seen, water demand. Fly ash reduces superplasticizer demand or plasticizer demand, I mean water reducing agent demand, rice husk causes increase. Fly ash may cause reduction, may reduce. So, if I sort of in a scale, if I want to put them in a kind of scale, fly ash would be one which shows much better performance at the fresh state or enhances the performance of the cement based material in fresh state compared to, let us say, other mineral admixtures. Inert mineral admixtures such as limestone powder or similar sort of thing essentially contributes to the paste in the system. Now, if we can recall, it is paste content, sometime we have just stated, we have discussed that in case of concrete system, paste is expected to fill in all the voids in the mortar, and mortar is expected to fill in all the voids in the aggregate system. So, inert powder contribute to the paste, and the paste, it is required that paste should be flowing. So, inert powders, they will always contribute to the play. Inert powder of cementitious size, of cement size, let us say, of compatible size with cement, with cement, contributes to paste and makes concrete more cohesive. If it is pozzolanic material, then also they, because of their sizes which is compatible with the cement or nearly cement size, they can pack well within the cement system. Therefore, they also contribute to the paste. Now, this has got in modern two types of concrete, this has got high relevance. For example, pumpable concrete, where you want more cohesion such that water, the slump required would be something of the order of 120 or 150 millimeter. So, when in case of pumpable concrete, fly ash increases the cohesion of the mix and water cannot get out of the concrete system when it's subjected to pumping. Otherwise, the water has a tendency to go out of the system, leaving the solids behind. This cannot occur if I have sufficient fines in the system. Therefore, in pumpable concrete, it is necessary that I have sufficient paste content to fill in all the voids in the mortar and slightly more, and the paste should be such that it can actually holds the water together and generate a fine slurry at the pipe concrete interface. So, that pumping becomes possible, friction becomes less. Now, such situation for pumping, addition of fly ash is almost a mere necessity, or very fine powders of the similar kind is almost a necessity. It helps very much. A second modern concrete where they become very useful is self compacting concrete, where the paste content is much higher. And when we talk about self compacting concrete, we will be talking about this issue at all again. The self compacting concrete, you need lot more paste. Now, you can't add on cement, because cement will contribute to shrinkage. There will be other secondary effects, heat of hydration. So, therefore, one would use inert powder or pozzolanic material like fly ash. So, fly ash, while in self compacting concrete or pumpable concrete or high slump concrete, where you need high amount of paste, relatively more amount of paste and flowing paste, addition of this mineral admixtures is almost a necessity. So, these two places where they act again positively, which right now we have not discussed in details. When we talk of pumpability, we will be coming back to it again, and similarly when we talk of self compacting concrete, we will look at this one again, we will look into the same thing. So, as far as fresh state is concerned, these two materials, these materials fly ash acts most positively. Rice husk ash of course do not act so positively, it would be the other end, and other materials like GGBFS and silica fume also do not contribute very positively to water reduction, etc., etc. Right. So, this is generally the performance of this material in fresh state. This is generally performance of mineral admixtures, their effect on fresh state. But what about early strength gain? When it comes to early strength gain, we have seen the reaction rate of fly ash is slow. Silica fume is itself is so fine that it can fill in the pore within the cement system right in the beginning. So, you get what is known as pore filling effect, thereby right from the beginning you might see there is an increase in strength or strength enhancement, early strength there is no problem. Whereas, if you look at fly ash, there will be some problem related to early strength gain, as that fly ash reaction starts only after liberation of sufficient amount of calcium hydroxide. So, when together with cement you use fly ash, early strength gain is usually less compared to no fly ash, whereas silica fume this is not the problem. And GGBFS also similarly, if you use GGBFS which can be used in relatively more quantity than the fly ash, early strength gain is not, you do not get the early strength gain, whereas long term strength would be fine. So, you have reduction in heat of hydration, and at the same time the moment you have reduction in heat of hydration, because of the reaction rate being slow and reaction initiation time being longer, as calcium hydroxide liberation has to take place. So, initial strength gain is relatively less in such material, but heat of hydration is also lower, whereas those material which will have high early which do not have that much of problem in terms of initial strength gain will not be very much effective in reducing heat of hydration. So, silica fume in that sense is not as effective as fly ash in reducing the heat of hydration, but it the effect on initial strength gain is also lower in this kind of this material. So, I think this should end up our discussion on fresh concrete and initial stage of strength development. In the long run, all this material tend to show better strength and durability characteristics because of pore filling effect, because of the secondary reaction, secondary hydration reaction which takes place over a longer period of time, that would tend to improve the microstructure in terms of improve the microstructure in terms of its soundness, that is reduction in porosity is the main issue, and therefore, the strength gain would see strength gain in the long run is more than the normal strength concrete. That is, for same 28 days strength, you will find that a fly ash concrete having same 28 days strength, long term strength will be higher. So is the case with silica fume, but silica fume can give an early strength no gain, or at least maintain the same early strength. GGBFS also is similar, in its 28 days strength being similar, you might find long term strength is better. This issue we will look into the next lecture. So, to conclude this lecture, we can see that we have looked into the effect of mineral admixture in fresh state of concrete in terms of heat of hydration, setting time, water reduction, and water reducing agent demand. Right, and we also talked about a little bit on strength gain, which we will be doing in the next class in more details in the long term strength gain and their effect on hardened concrete system. So, with this we can conclude this lecture. Thank you very much.